session?
Yeah, exactly. Oh, they thought it was a study session? Get memed on it. Wasn't.
Exactly.
Hey guys, I gotta go.
People joining the chat like, man, why are they
All
all
right.
shirtless?
Gotcha, Jacob. See you.
No, I was kidding, man. I was kidding.
Yeah, all right, easy peasy. So, all right, well, if we're gonna address this stuff, then we'll address syntax stuff and we'll discuss why things go where. So I guess we'll start off then. So first things first, with regards to the syntax stuff, everyone here has a decent understanding of C++. Like, you know how to write this part in C++ and what it does.
Oh yeah.
Yeah, okay,
Yeah.
good. That,
Yes.
hopefully anyone in this class should understand how to do like basic like for loops and like initializing arrays and stuff and such.
Yeah.
If else, all that stuff. All right, so the first thing is, in ARM, we don't have the luxury of getting to just write for, if else. We have to do it in a wacky way. We get to write loop. And that's not even actually a command. This is just a initialized branch. What are they called? They call them labels. So we don't get to do that. So the first things first, when we go down through this, we have to do, like any other programming language, we have to declare things. So we have to declare constant int size, this is just used as the upper limit of the initialized variable I, the control arc. So once it reaches 10, since I is less than 10, it stops in the for loop. So we have to figure out how to do that over here. So we do same thing, same place. Here in C++, you'd say constant int size and you have 10. Down here, you just give size as your label, DCD, and then 10. And then that's about the same for everything else when it comes to just addressing values, like giving these things values, but initializing these as locations in memory involves these commands. ADR is reserved for when you're, ADR is reserved for when you are initializing an array into memory. So whenever you see, X, Y in this case are our arrays, ADR is used for initializing like large chunks of data as opposed to a singular value. Like you can see I, you load into R0 the value of I, which in this case is predefined as 0, but it gets incremented as we go. So load normally just stores, one variable. You can't use load to load an array, I'm fairly sure. I don't believe that works, which is why you use ADR instead. And then the syntax across all of these commands is what it's doing, where it's going, what's going in here. So that's across the board for everything. And that's an important thing to understand. So like if we were to put in ADR R10, we're loading the entire array of X into R10 using ADR. If we did load R10 with X, it either wouldn't work or it would simply load 8. So you don't want to use load when you're trying to initialize arrays. So then the, next step? So we go through, so we use ADR to initialize an array. We use load to initialize a variable. We use load to initialize yet again another variable, which is size, which in this case has been given the value of 10. ADR again for another array. And this one is a bit important to understand. So we have ADR Z, which is another array. But in the C++ code, the array Z isn't given. It's not given values like these ones are, where they have predefined values. We're populating Z with the operation from the for loop on X and Y, which in this case, the operation is simply picking the larger of the two numbers. If X is larger than Y, you populate it, else Z is equal to 1. So down here, if you want to create an empty array, you have to use ADR R12Z, and that'll initialize an empty array. But then you need to pre-allocate space for your array. This is important. If you don't pre-allocate space, you run the risk of having some problems later on with your data, because it either will overload it because it doesn't know how much space it has, or it will underload it yet again because it doesn't know how much space it has. So that's what this whole space thing is for. So when you're trying to initialize empty arrays, you have to use space down at the bottom and initialize it. So we go down here and we see Z space 40.
Can I raise my hand?
Yeah.
I know this is hella informal, but
Yeah.
but
yeah, you can do for future reference. You can just talk. I'm chewing gum right now. Like you can go.
All right. So can you scroll back up to the C++ code?
Here, I'm gonna use my thing so I can get it all in one frame.
Yeah. So I guess from So from the area part, where the actual like code is being written, like the ARM code
Yeah.
down to about, move R3, R1. So is that just initializing the code for, that's just initializing the memory for ARM?
Yeah, that's initializing your labels. So there's actually a couple different places. So you see how here we just get to write this, like int x size, and then array with the size being 10. So this whole thing is initializing just x, right?
Yeah.
And then this is operating on x. In ARM, it's split up. It's split up. So here where you did this int x size thing, we're doing ADR R10x is the first step in initializing your array x. And then down here is where we load the values in for x. And same for
okay.
y. So it's not all in one. We don't get the luxury of doing it all in one go at the beginning like we would over here. Because this, as you can see, is much more concise and easy to read. You're like, oh, size 10. So x is a array of 10, like 10 units. And here are all the values in those 10 spaces. Cool. Over here, we tell the computer ADR means we're reserving the array. The array is stored in R10. The array's pointer or label is X. Go down here. Oh, here's the label for X. Okay, what's next? DCD. Okay, we're getting numbers here. Here are these values. Okay, so that's how many values are being initialized into X. Now here's the thing. You see how in this one, we get to say int x size, and size is equal to 10, so it knows that it's expecting 10 values here.
Yeah.
In ARM, it's a bit different. We don't see that anywhere. Size here is declared as 10, but size here is strictly used to control, it's loaded into R1, is strictly used to control the loop. Where is that? So we have R1, so we're looking for where R1 is. So we're using this to control this compare statement using to control the loop. R0 is I. So the only thing size is used for in the ARM is once I reaches 10, the loop terminates because you're comparing 10 to whatever value I is, which it starts as 0.
So what's the difference between the like the first, I guess, column, like LDR, ADR?
So LDR, I'm fairly sure is loading like a variable value. So like I could have however, so let's say I had like the value of I is like 300 something, or just some random hex string that's less than 32 bits.
Yeah.
So I can load that single hex string of however big, as long as it fits within the parameters of the computer, into the register, which is 32 bits traditionally. At least that's how we're working with it. If you tried to use ADR, or if you tried to use LDR to load an array of values in, I haven't tested it, but I'm pretty sure it does one of two things. It either doesn't work or it only loads the first value.
All right. So ADR is for arrays.
Yeah, ADR is for array. I remember that by just a array.
And is R10, is that special, or is that just like a variable name?
Which one?
R10 from the first one.
This?
ADR. Yeah.
This is the register. So we don't get to name registers. They exist.
All right. Is R10, is that like the register for arrays?
No, you can use.
You could do R1. You could do R0.
Yeah, if you wanted to.
Yeah, you can pick any register. That's just the one that she picked on that example.
Yeah.
But if so all the blue stuff, I'm assuming, is what we have to fill in on the test. So if that's the case, she's picked that register. So you'll have to still use register R10 when you go into your loops.
Oh, okay.
Yeah. So I think she does us the solid on exams, as he said, of giving us this part, and we have to fill in the intermediate, which is she gives us the variable declarations, the values of each of them, and then says, all right, now I want you to perform the operations using these variables. So the reasoning behind that, obviously, ease of grading, because as Ron said, you can use any register you want. This could be 0, but this could be R0, this could be R5. If that were the case, like every student would have their own preferred method of design, like designating registers, and that would just get a little confusing. But
Yeah.
you're not restricted to using R10 for registers or such. She just chose to.
All right.
Yeah. So the big difference here is like, ARM is, long-winded. This type of code is, high abstraction, C++ code, like traditional coding language is high abstraction. ARM, in my opinion, is like an intermediate I keep saying ARM, but I mean to say assembly. Assembly is like an intermediate between high abstraction, relatively common coding language and machine language. Like it's closer to machine language than traditional high abstraction because this is a lot simpler. But this is more powerful because you have more direct control over what happens. Because you get to control each element more precisely. At least that's what I've seen. So we were back talking about.
Yeah, so we got everything that she's put in, and we understand that. Now we got the right thing.
All right. Yeah. So as you can see here, we haven't used R2, R3, or R0 yet. Wait, we did use R0. I meant to say we haven't used R2 or R3. So these R2 and R3 have not been used yet. So this is the first thing where a student could pick any register if they so desired. This could be R4. This could be R5 if they wanted to. So move in this context is simply loading the value of 0, which is a constant here. So when you want to load like a number in, you don't get to just type like 8. In this context, you can do it when you're doing array designation, but you'll see every other time when using move commands or any of these commands, you have to use the hashtag, I'll say, or pound sign, and the constant number you want to throw in there. So move R2, like #0, all that does is apply the value of 0 to R2. Now, if you were to use R2 anywhere, which we will, like here, it'll have this value in it until it's operated on. Then over here, we have move R3, stores 1. So now we have R2 has the value of 0, R3 has the value of 1 for later. Now we start here. So unlike C++, where we can say for or if, and these are designated terms that actually have a meaning, this could be hot dog for all we care. We get to say what this is. We get to pick the labels here. So what happens here?
So what, loop could be hot dog?
Yep, that's a label. So you could make that whatever you want, essentially. Loop is not a defined term here. So it's just because what this is actually, so it's a little confusing about about ARM, is that we're trained to like do things where, oh, like we write this, then this is operated on down here, and we'd like to do things sequentially, where ARM jumps around. That's the whole definition of the branches that we're going to use quite often. It jumps around a lot. So loop is written up here, but loop is only used down here. Because what happens is when we run through, do all these operations, we reach branch. What does branch to? It goes to loop. Oh, where does the machine remember loop from? Up here. All right, start here, do this again. That's all branches do. It just, you have your branch, it points somewhere, jumps back, and continues. Hence the reason this branch, as you can see, is a statement that ends the loop. What does it do? You reach the branch. Where's the branch to? Done. Where's done? It's there. Oh, it stops. So this is why this ends it. So now we've reached a loop. So that's just a point home. Same with done. If you wanted done to be anything else, you could have it be something else. You could write hot dog here, and it would do the same thing. So we're at the label of loop, and we're at the compare statement. So the compare statement is initializing our control variable. This line right here, compare R0, R1, is functionally the same as the for control architecture, but it's really this specific portion of the control architecture for the for loop. So this compare statement is essentially performing the same task that this I less than size statement is performing in the for loop. So what does compare statement do? Compare statement simply takes first value subtracted by this value, and you use this to set the 0 flag. That's important because if this value is equal to this value, your 0 flag will be set as 1 because 1 minus 1 is 0. Any number minus itself is 0. And you can use the fact that this will create a 0 flag shift if the numbers are the same as a method to control for whether or not a variable is equal to. And that's what we essentially end up using here. And that's what we do with it.
Where'd you get this document?
This is on course module. Scroll down in your modules. I went too far. Scroll down in your module, scroll up. Test one solutions. All of them are here. And this specific document, I believe, is this one. Yep.
All right, cool.
Now I gotta find it again. There it is. So we're at the compare statement. So the compare statement simply sets the value of your zero flag, and you can use that as a control variable, or not a variable. You can use that as a control value or controlling logic for your loop. So then after that, we set our zero flag. Cool. Next thing we go to, branch greater than or equal to. So this is where we use that cool stuff where you can add comparison logic onto other things. You can do conditional execution with the branches. So traditionally, if you just wrote branch, it would simply branch over here. It would branch to whatever label you put after it. And as you can see, branch greater than or equal to branches to done. So there's two separate instances where branch to done occurs here, because every time you branch to done, that's a termination. Instance. If you see a branch to done in this loop anywhere, it's going to end the loop. It's going to stop the code because it comes down here and stops itself. So what does this mean? Branch greater than or equal to. So this greater than or equal to is essentially comparing this greater than or equal to is comparing the value of I to the value of size based off of the compare. Because if we go, what is R0 and R1, if we remember, R0 is I, R1 is size. That's what our compare statement initialized as. And then after that, the branch greater than or equal to is simply testing if I is greater than or equal to size. Is it that way or is it the other way around? Let's make sure. Yeah. If I is greater than or equal to size, it conditionally executes, goes to done, finishes, because that's one of the termination requirements over here in the C++ code. If I is less than size, it stops the for loop. No, if I is less than size, it continues. Once I is greater than size, it stops. And here's something she said a lot in class, where in ARM, we tend to use the opposite. We test the opposite condition as we would in C++. Because here, this for loop has logic built into the command itself that always tests for this logical condition. And this is a run while. So as long as I is less than size, for loop continues. In this instance, we don't have that luxury. Instead, we have to write out the termination condition. We only test for one thing. We don't use this to continuously test. Well, it will test, but it tests for one thing as opposed to saying this, if this is true, it keeps going. If this is true, it stops. So in ARM, we test for the opposite condition most of the time when compared to C++. I don't know exactly why we do it that way. It's just how we ended up doing it, I guess. It's how we were taught how to do it. So, and it seems to work. So we'll just go with it like that. So all we need to know about these things is when you're initializing your loop systems, you always want to start out with a compare to set your flags, and then immediately follow it up with the termination condition of the loop, which in this case is when I is greater than or equal to R1. So then we immediately go down here to the next term. So this is load. So this is augmenting an intermediate variable. As you can see, we haven't used R4 or R5 anywhere yet. So these are new registers that are, as far as we're aware, empty. So we simply perform the operation in here. So when you see these brackets and you see this is for the effective address is what we're doing here. Wait, is this effective address or is this no? This isn't effective address, I think. This is pulling out the index term out. So here's what we do. R10 is X. So the first thing it does, I'm going to pull out my annotation to show this because I have to write this out. It's probably better. Let me lower my DPI. All right. So this operation R10, R0, LSL1 is functionally the same as R10 plus R0 LSL by the constant 2. So R10 being X, whatever value in X, R0 being I, whatever values in I, and R0 logical shift left by 2 elements or by 2 variables or yeah, by 2 bits. And this is going to load into R4, which is used in a compare statement over here. So let's run through and see what would happen if we did this. So let's take the first value of X, for example. First value of X here is 8. So we have 8 plus, let's say this is the first time it ran through. So R is, R0 is still 0. 0. Logical shift left by 2. If you logically shift 0 left by 2, it's still just going to be 0, 0 then. You're just increasing the amount of zeros, but it's still going to be 0. So we would load R4 with simply 8 in binary, whatever that's being stored as. And that's what R4 gets. We go down to R5. R5 is functionally the exact same thing, but it's simply using the values from Y instead, performing this operation on it, and then loading it. And I'm pretty sure the reason we perform this operation at all is because it produces the effective address of the term we're looking for. Or if not the effective address, it allows us to increment what entry we're looking for. Oh, never mind. That's exactly how this works. All right, let me bring it all back for you. You guys remember how we say everything's byte addressable?
Yeah.
Everything's in chunks of 4. So what that means is you guys are aware that, 8 is represented. Did I say byte addressable? 4 byte addressable, right? It's chunks of 4 bytes. Sorry. Because 4 bytes is going to yield you 32 bits total. So that's how we're working here. So when you logically shift left by 2, that's multiplying, functionally multiplying by, what is it? Multiplied by 2? No. Yes. Logically shift left is multiplying by 2, correct? Does anyone confirm or deny that? Because it's moving you over by powers of 2. So if you have 1 and you logically shift it left twice, it gets 2 zeros. Now it's functionally 4, multiplied by 4. All right. Logical shift left is multiplying something by 4. What that allows us to do is when we look at this, we see one number, right? So we'd be like, well, why would we shift the entry by 4? That would get us 7. But that's not how the computer sees this. The computer sees 8 as its binary string. So when we logically shift left, this register is holding several separate binary strings, which take up several little spaces. The logical shift left is simply jumping all that excess that's in technically part of 8, but isn't actually useful, skips all that data and moves to the next one. So this command is what allows us to, as we increment through, because it has a control variable of the incrementing value of I, allows us to shift to new values each time as we move through the loop. So these commands, these things, you can see it's used the exact same way everywhere. Whenever it's used, it's literally LSL, your control variable, and then whatever variable you are trying to increment and pull a new value from, or in this case, store a new value in. So this is a very important thing to understand, which is that you're using LSL to essentially multiply by 4 to get to the next entry in your arrays. And that's what that's for. And we're loading these new registers with the value each time. So functionally, the first time this loads 8, the next time this loads 2, the next time this loads 9. And that's what it does. So this doesn't actually augment or change the values that we see in our arrays. It simply loads the new one in each time. We use this as opposed to this. In C++, we just get to say X, the number we want. That's real easy, isn't it? Compared to having to understand this. Luxuries we get in C++, we don't get in assembly, I suppose. And that's the same thing. So when we're doing load here, we're simply loading in the value of 8 at any given time, at any given point in the loop for different values of I, which is R0, loading that into R4, and then for Y, for different values of R0, loading that into R5. Cool. We go to a new compare statement, which is comparing the values of 4 and 5. In this case, it's doing X minus Y. to set more zero flags. Because look, here's something that's important. Can anyone tell me what this compare statement, where this compare statement will be found in the C++ code?
Yeah, R4, and what is that? R5.
So this is testing x minus y. So this statement is x minus y. The only thing a compare statement does is set the zero flag. So actually, the only thing that this compare statement is for, it's actually very important. What happens in this if x and y are equal to each other? Well,
They equal 1.
we trip the else, yeah, and set it equal to 1. Here, we don't have else. We need to figure out how to do this somewhere else. If x and y are equal, the zero flag here for compare set to 1. Boom, done, you did it. You stored the zero flag. That's what this does. So that's just the else condition. If this weren't here, it's not shown here, but if one of these values at the same entry were the same value, we would run into problems and we would start having issues with our conditional logic. It would probably skip an entry and you wouldn't have 10 populated entries. You would have an empty entry, which is not good. So this compare statement can functionally be tracked back to this else statement. After that, we start doing the conditional logic of this part. This is where the if statement's conditional logic happens. We have store greater than and store less than. So R2, I'm pretty sure that's another, no, R2 is where we initialize the value of 0 and 1 previously. So we have R2, and we're storing the greater than. So store greater than essentially is just doing conditional logic of whether or not something's greater than, so it compares. So let's go through here. Yet again, R12 in this case is our Z. So this is the empty array with space of 40 bytes. Yeah, 40 bytes, 4 bytes per entry, 10 entries, therefore 40 bytes. That's why we have the number 40, by the way. So we come down here, store greater than. So R2 currently has the value of 0. R3 currently has the value of 1. So we go through. Does anyone remember if store, I know that load would be functionally written as LDR R4, let's just say R4, R10, would be functionally written as R4 receives R10. One for load. But would that mean that store would yield us the opposite of that? Does anyone remember that from the homework? Like store, if we did store R4, R10, would that do it this way? It pulls whatever's from here in.
Yes, I believe so.
Yeah, we can check that real quick because I have the other stuff open. Boop. Boop. That's not the right one. Here we are. Huh. So here's a store, R1, R2, R0. So this stores the position in memory sum of R2 and R4. It stores R1 into the memory address here. Yeah, so that's what it does. So that's important to understand here too, and I'll show you in a second why. Because if we were to not understand that the store command is fundamentally different from the load command, we'd make a fundamental error here, because what ends up happening is here we're taking the result of this and loading it into R4. Here, if we took the result of this and loaded it into R2, that's pretty useless because R2 has nothing more than a 0 in it right now, and it's also initialized as just a register. It's not it doesn't have a pointer or a label. It's just a register with a number in it. So this would be fundamentally pretty useless to us if we were to load the values of R12 operated. And here's another thing. Remember, R12 is the empty array Z, so there isn't even anything in it yet. So what happens first? So this again, remember previous that this simply allows you to increment the entry. So at the bat, first loop through, R12, R0, LSL is simply gonna, populate the first entry of R12 with whatever is put in R2. Still greater than R2 and R3, and then this one's similar. Now that I'm looking at this, I feel like these two are a little messed up. Because store greater than R2, we simply moved constants 0 and 1 into R2 and R3. So we do this, we compare, we do R4 minus R5, that sets our 0 flag or whatever, and that's our else condition. But we hop down here for the store greater than, which is comparing, greater than or equal to, no, this is just greater than, then this is less than or equal to store LE. R2 and R3 aren't changed anywhere else but here. They just have constants. And the reason that's a problem is we just compared and found out that store R2 is going to take whatever's in R2, store and compare it greater than, take what's in R2 and put it here. Wherever this reduces to, whatever entry of Z this becomes, it puts it in. R2 isn't changed anywhere. The values we're changing, we're loading R4 and R5 with intermediate values from X and Y respectively. So I'm pretty sure that these R4 and R5 are supposed to be in R2 and R3. Let me check something. Because if we remember, we did an in-class assignment. Keel, where are you? There you are.
I like the Minecraft.
Heck yeah, dude. You're like, I have Castle Miner Z.
You know what? That's a classic.
It is a classic.
I think I had that on the Xbox 360 back in the day.
That's what I have. Huh, this is for something different actually, but let's see. Huh. So this is something I've done before, initialize variables, branch equal to, load, add. But this is a different loop. This is for the other homework assignments. This isn't right. The one that we did in class recently has this, and I'm trying to remember, because the reason I think this is a little off is these intermediate values are what's being stored into the memory address. So I feel like we need to find out what's being compared to greater than here, store greater than. Does anyone remember that using these? Because even I'm a little confused at this point with the store greater than and store less than here, because we've only initialized move R2 and we've put 0 into R2, and move R3, we put 1 into R3. The only time we use R2 and R3 is in the store statements. And as we just confirmed, store takes whatever's in here and moves it into the memory or location address that this produces. In this case, these simply produce entries. So I feel like there's a little bit of a disconnect how we're taking the X entries and moving them into the Z.
You compare R4 and R5, and it stores it in ZI equals 0, ZI equals 1. It stores whatever you had before it finishes the loop and starts over.
Okay.
That's why I think it does.
So it's based off the compare statement.
Yeah.
All right.
It'll store whatever's greater than and then whatever's less than, and either or. I don't know what the add does though.
I know what add does. Add is incrementing your I.
Yeah. Okay. It makes space. Okay.
Yeah. Add increments the I. So here it looks like there's a requirement of intermediate variables or intermediate registers with values here as part of the store. This is the comparison logic greater than or less than. And you can
Yeah.
see that they're both loading into the same position at any given time. The same way that these ones are pulling from the same entry in their respective arrays, except they're putting them into different, they're pulling them from different arrays and then putting them into different registers. This
'cause
one is different. It's
is.
pulling from the same, or it's storing into the same location in the array at any given time.
Yeah, that's why I think it's zi equals 1 or z else essentially zi equals 0 or flip that zi equals 0 else zi equals 1 because R12 is z. So
Yeah.
z or 0 is I, so that makes it zi, and then you shift it.
Yeah. So it shifts everything in there.
Yeah.
Yeah. Because then after that, the only
Yeah.
only place where actual operations take place is essentially this part. These two lines right here are performing this operation essentially.
Yeah, and then it's performing that operation and then it's storing into either or zi's. Yeah, that zi or the zi under else.
Oh, never mind. Okay, I'm starting to understand something. So remember how I kept talking about how this was similar to the home or the assignment that we did in class?
Yeah.
So you guys remember how the assignment in class, we were storing the value from X or Y that was greater than?
Yeah.
Yeah, so here's a great rule from here on out. Make sure that you like read instructions, or at least read the C++ code. Because look, if X is greater than Y, no one cares what these values are. You don't store them. You simply put a 0 into Z. And if X is not greater than Y, you store a 1 into Z. Guess what that means? That's what the whole point of these variables is. Now that we know that that's the point of the variables, store greater than. This is based off the flag here. So here's what we know. R4 minus R5, X minus Y. If X is greater than Y, it will be a positive number. There will be no flag set. Therefore, store greater than will operate and store R2, which happens to be 0, into the respective location in the Z array, which is, boom, what you're supposed to do. Go back to the compare flag. R4 minus R5, X minus Y. If X is equal to Y, it'll set the 0 flag as 1. If X is less than Y, it will set the negative flag as 1. That means 0 or 1, or 0 flag as 1 or negative flag as 1 will cause the less than or equal to clause to operate instead of the greater than clause, storing R3 into the respective value of Z, which guess what? R3 happens to be 0 or R3 happens to be 1, fulfilling the else condition. So previously when I said this was the else condition, I was wrong and right. This compare statement essentially runs the control logic and sets the flags, which carry through and are being operated on by the store statements. So this does everything. Okay, so now I understand what's happening there. That makes a lot more sense. Does anyone need a better explanation there? It probably was a little rambly. Like for the, because functionally in this code, the most important part of this loop being the if statement, like the actual logic, in terms of like ARM assembly, a for loop is very, very easy because you simply use a label, a compare statement, and a branch statement. Then you're done. And then you just initialize those at the bottom. This is where we get some complexity because then we have to use all this wacky stuff like conditional logic storing and then understanding how flags work, hence that homework assignment we just worked. That emphasized so much importance on flags because as you can see, your conditional logic controls that you append onto the end of these statements are dictated and controlled by the flag results from this compare statement. So that's why it's very important to make sure you use your compare statements right. So does everyone get why this works now, why this code functions, and how it corresponds to this code?
Yeah, for the most part.
All right, cool. Yeah.
Makes more sense now.
Yeah. You could definitely see that I had to explain it to myself halfway through there because I didn't actually know it completely until that last thing where Ron said something that gave me that eureka moment. And that eureka moment was I don't read instructions. Big man. All right. So that's how this works. So we, and then we'll just finish it off.
Yeah,
So
the same way.
yeah, so add increments your I, cool. So this add statement is essentially this thing. Yay. We go there, we do that, go down. Okay, cool. We've hit the branch loop. What does that mean? We go up to loop, we operate again. And we keep operating until this compare statement sets the zero flag as 1. Because when it sets the zero flag as 1, it'll terminate because this greater than or equals to flag will see the zero flags equal to 1. Therefore, R0 and R1 are either equal to each other, which they will be equal to each other first, or greater than each other. You see that flag set, branch to done, branches to done. What happens next? Branch to done, branch to done, we're done. Because it's just going to keep doing this thing and it'll terminate eventually on its own. So that's the completed understanding of the student written portion of the code, as well as the initialization, because this is, while in terms of the likelihood of us having to do this on a test are low, because it would make it more difficult for grading on her part. So most likely we'll be given these initializations, but it's important to understand how to do the initializations because we're not learning this to take a test. We're learning this to actually understand and utilize it in the real world. So understanding how to initialize and set up the code is just as important than how to write the functional logic of it. So that's that. So does anyone have any questions on like the register transfer notation stuff? This stuff, like performing rotates, arithmetic sums, logical shifts. Of all of them, this is a joke to perform logical shift. This is a little tricky actually, but once you understand that whole copy thing, it's not as bad. And then this one seems tricky, but in my opinion, it's the middleman. Logical shift being the most easy to understand, arithmetic sum right being the most complex to understand, and then whatever this is actually say, I just call it rotate, being the most intermediate to understand. You simply just take this over here and just go and keep doing it, move everything over like a conveyor belt. Is that, let's see, everyone understands how to do this stuff by now. Also, if you guys remember on the homework how she said like don't assume, just assume it's neither, it doesn't matter, and it caused a lot of confusion. You can see that on the test she gives you assumptions. She tells you what to assume. Choose complement representation means signed, which is good. Wait, does it? It doesn't necessarily, never mind. It'd be signed to complement representation, but either way. Setting flags is important. As we just saw in the code, flags are essentially what controls the code. So you need to understand the best way to set flags and how to set them in your benefit. Then there's this, which is conversions, easy peasy. More conversions, yet again, pretty easy peasy. This is what we just did. So are there any other questions with regards to stuff like this?
Wait, stuff like the like writing code or stuff like in general in the class?
Just anything. If you have like code writing questions, I can try my best to answer some.
I don't even think I got it like a right last night when I did the number 3 from the homework.
Number 3?
Yeah.
Number three. I can pull that up and we'll look at it.
Well, so number 3 on the homework, I ended up asking her about it when school was out. She you have to essentially you flip it from signs to complement. Let me look at it.
Here we are.
Yeah, so you convert negative 160, and so you just convert 160 by 2, divide all that by 2.
Oh, that's number 4.
Oh shit, yeah, you're right. Never mind.
Yeah.
Never mind. Sorry, me.
So here's number 3. First off, I asked her this question. As you can see, R2 is used nowhere. This means nothing. You can simply ignore it. So we're given this hex string. So this hex string, 1 hexadecimal value is comparable to 4 binary values or 4 binary levels. So, A is equal to 10, so it's 1, 0, 1, 0, and so on. So looking at this string, in terms of binary digits, this is 32 digits. So that's something important to understand, because while it's possible to operate exclusively in hexadecimal, if you so choose, I don't recommend it. Unless you're working like this, because this can actually interestingly enough, if you're operating like this, logical shift left to 4, particularly logical shift left to 4, you can actually leave it all in hex. So it says, what's the value of R0 after each of the instructions has been executed? So functionally, this instruction is asking you to do this. We'll do A. It says add R0, which is where it's being stored. Hence the reason it's asking for the value of R0. And here's where the math starts. R1, R1, logical shift left 4. This is asking you essentially to do this. We have R0 will receive the value of R1 plus R1 LSL by 4. By 4. Let me just add a terrible little hash sign there. So that's what's happening here. So functionally, as I said, I hinted that operating on hex with these things can be complex and not recommended. But in this case, I think for A, you can leave this in hex and never convert it to binary. And as I said, we know that one value in hex is equal to 4 values in binary. And this is shifting us left 4. So the first thing you should do is generate this term, because we know this already. So we need to find this term before we can add it. So LSL on R1 is A5362C89. We know that logical shift left is appending zeros onto the right and pushing values off of the left until we've moved over the specified number of times, which is 4 here. That means we can do something pretty funny. A is composed of 4 values, binary 1, 0, 1, 0. So guess what? A drops off. We're done there. What's next? 5, shift over, shift over, shift over, shift over, shift over, shift over. What's this next entry? All zeros? Cool. That means our new R1 after LSL 4 is 5, 3, 6, 2, C, 8, 9, 0, because we appended 4 zeros. Hexadecimal for 0 is 0, 0, 0, 0 in binary. So this is this, and then you simply sum this with this original one, so A5362C89, and you can decide if you want to do this in hexadecimal or in binary. Personally, as long as you understand how number systems operate, you could do this part in hex if you so choose, since you already have the 2 values. Do you know how to, like, are you good with how to add these together? Like just adding A5, 3, 6, 2, C, 8, 9. Like how to add this together? Like this would be 9. And then functionally, you can only approach so big a number, like F or whatever. And F is equal to 15. And so on and so forth. So you just go over.
Is it that easy? Because I always just converted it to binary, so I didn't fuck it up.
It's best to convert it to binary, definitely, because like hex has its own rules for adding, subtracting, and such. So converting this to binary would make it the easiest. But the reason that I have it in hex in the first place here is just because the logical shift left is easy to do in hex simply because it's by 4, which is essentially the adding the hexadecimal value of 0 onto the right hand side and pushing the hex value A off the left. If this were 5, we would have to do this in binary.
Oh, okay. Yeah.
So does this part make a little more sense, Jordan? Essentially how to do it is easiest, convert this to binary, perform these operations first, then add them to their original value, store them into 0. So arithmetic sum right of 8 of R1, if we converted that to binary, we simply take the first digit of the binary value of A, which is 1. The most significant bit is 1 for this whole string. We take that, we copy it 8 times, append it on, and then we start adding zeros. And that's how you do that, sum it on. And then for rotate 7, you simply take this, convert it to binary, and then start shifting the values. Rotate's the only one that doesn't lose information. So you're simply carouseling the values around. Whatever drops off one side pops up on the other sequentially. And then you do the same operation where you take whatever the result of this operation is and add it to the original value and then store it. It's not that difficult once you understand what it's asking, because it's a little confusing, but it's not that bad.
Do you mind going over 3B?
3B, arithmetic sum, right? So let me turn off this thing. And I'm still drawing. That was pretty useful. All right. Where is this? Nope. This one. So 3B is arithmetic sum right. 8. So I'm going to pull out a piece of paper and say this out loud and such, because honestly, writing with a mouse is horrible and I hate it. So we have add R1, arithmetic sum right 8. So the first things first for B, as I said A, because it just so happens to be an increment of 4, you could theoretically leave the whole thing in hex if you so choose, but best practice is to convert this to binary. So converting R1 to binary is it's going to be 1 0 1 0 5 5 3 6. So 5 is going to be 0 1 0 1, 3 is going to be 0 0 1 1, 6 is going to be 0 1 1 0, and then 2 is going to be 0 0 1 0, and then C is going to be what is it? A is 10, so C is 12. So then C just yields 1 1 0 0. 8 is 1 0 0 0, and 9 is 1 0 0 1. So now we have our binary string of R1. So good news, if you convert R1 to binary, you already have half of the problem complete because you have one of the components of the addition complete. Now we have to do the arithmetic sum right 8 values over. Now the reason I opened up that other thing is this is a million little examples of how to do an arithmetic sum. So here is one where it's actually, this is basically right here, what we're seeing right here is 3B, just with a different hex number to start. Because look, R2, while given, isn't used. It's R1, arithmetic sum by 5 instead of 8 here. So here would be our number instead. So, 1 0 1 0 whole thing. And then we have our arithmetic sum right. So here's the pattern for arithmetic sum right. It's shifting this over to the right, hence arithmetic sum right. Now, as opposed to left shift, logical shift left, it's not as simple as appending zeros to the left-hand side to force everything off. While this is still going to lose values by forcing stuff off the right-hand side, it's not that simple. So this is by 5. So let's look. We're going to lose 5 values. Here are 5 values right here. We lose all of this data. Pushing it off, and you can see we have 4 zeros. Those 4 zeros happen to be these 4 zeros. Push it off. On this side, our first bit here is 1. Wrong. Our first bit is 0. So we add 5 zeros. Now, if our first bit is 1, like it is in the practice problem here, converting this string to binary, the first bit is 1. The arithmetic sum right of 8 happens to just be 8 ones followed by the old values. Wrong one, followed by the old values. So here we see we have 0 1 0 1, yeah, 0 1 0 1. Cool. Here is that same 0 1 0 1 in the next value after we perform our arithmetic sum right. So you can see that the values are shifted over 5 But logical shift left, you simply add zeros every time. It doesn't matter. Arithmetic sum right, you add whatever the leading original bit, most significant bit was. In this case, it's a 0. In this example, if it were a 1, instead of zeros leading this, these would all be 1s. But this is still the same. You just lose data off the side. So the only difference between arithmetic sum right and logical shift left is, well, first off, they push this in different directions. But the real thing is what you're adding on isn't always zeros in ASR. It's dependent upon the most significant bit of your original value. So the most complex part of this is always performing these operations. The sum part, I'm sure everyone knows how to do binary addition at this point. Once you've got this value, it's very, very easy to just add through, and converting to hex, I'm also sure everyone understands that. So do you have a better understanding of what this is asking now?
Oh yeah, it makes more sense. I got the correct answer. I just wanted to get a better understanding of it because I had to look up the answer. I wasn't exactly sure on how to do it, but that helps.
Yeah, so the arithmetic shift right operation is simply adding, or adding however many numbers it's asking. In this case 5, but it could be 10 and anything. It could be 1. And you simply copy the most significant bit of the operand, whatever this is, take it, and that's what you're adding on. If this were a 1, these would all be 1s. And let's see if they have an example. Here's one. Arithmetic sum right 5, the leading bit here is a 1. So we have 1001. Let's look for the 1001 shifted over 5. Here's the 1001. Instead, we have 1s populating instead of zeros. That's all this does. So boom, bada boom, easy peasy. Back to the homework. Any other questions on these types of things, like effective address, effects?
Oh, you can hear me. My bad. What about the number 3 on R001? Where's the example for that one?
This one?
Yeah, if there is one, you got one pulled up.
Oh yeah, there is one. It should be in these last ones. This is the rotate rights. So here are the rotate rights. So this one has us rotate by 12, which if you remember, well, for rotate, it doesn't really matter. Rotate's fundamentally pretty easy.
Yeah, I imagine it's just like you just go over 12 and then you just look back around.
Yeah. So here's the original value. So now let me remember something. So we're looking for repeating 3s, because on the front, I'm pretty sure whatever's on the front drops off this side and cycles back. So shifting 12 would mean shifting 3 whole units over and appending them to the front. So shifting 12 would take this portion, these 12 digits, copy them to the front, and then shift it back. So if this were true, that means this would populate the rightmost portion. Boom, it does. So this one doesn't lose any data. This one just takes whatever this bit is, pulls it off, shift everything over to make this the least significant bit, take the 0, pull it over, slap it on the front. Next one, this is now the least significant bit. Take that, pop it off, push it over. Now here's our new least significant bit. Take this, pull it over, pop it on the front, and you repeat however many times it wants. So this one loses no data. The other ones do lose data by kicking it off the end. But these ones, this does not lose data because it simply takes whatever bit was on the end, on the rightmost side, pulls it off, pops it onto the leftmost side, and continues. It's like literally is a conveyor belt if you think about how conveyor belts work. In fact, a really good demonstration of this operation would be to print out a binary string and put it on a conveyor belt and just turn the conveyor belt on. Except the underside of the conveyor belt would have to instantaneously teleport. So that's a little bit difficult, but regardless, functionally the same. So that's how that works. So any other things? So this is 3. So these are all the logical shift left's pretty the simplest of them. This is the most complex of them. And this is the intermediate. Then this one, yet again, some value that is not needed. Like we didn't use it. Never mind, that's a lie. We do use it. Sorry about that. So functionally, it's saying what's the effective address. So it simply says perform this operation, which happens to be R2 plus R3 logically shifted left by 1. So you convert this to binary, logically shifted left by 1. You sum these together, load them into R0, and this is the effective address in hexadecimal. So you take this binary string, convert it to hex, and that's the address that loads into R0. So that's what that does. And by the way, there are examples like this whole homework assignment. Like if you go to her past like test thing that we that I pointed to earlier for review later on, if you guys want to go back and personally do some stuff, this thing, this test one solution tab, has not only like this has everything. Like this has examples for the
everything.
it has yeah, it has examples for the homework problems that we've done. It has examples for the coding problems that we've done. So as she said in class, functionally we can assume that anything that's done in homeworks is fair game on tests. So essentially reviewing her homework and reviewing her test solutions, which are technically just homework solutions, you should be in good shape for the test. Like particularly if you understand, like now, if you could get handed, you know, some arbitrary C++ code and write a decent approximation in ARM, you're in pretty good shape. Because if you understand how to do this, then functionally you understand how to do everything else. Because this is where you string everything together. This has effective addressing, it has loading, it has performing logical shifts, it's got everything. It's got addition. It's got loops or hot dogs, whatever you prefer. It's got it all. So that's that. So are there any other questions with regards to any of these? Yeah, I like this thing. Oh, how about this one? Anyone have any trouble with this one? Number 6. Yep. I just realized, chat. I just looked at the chat, and I saw that you were answering my my mild confusion with regards to the coding question earlier until I had my eureka moment and realized I didn't read the instructions.
Dang, you know, weren't you the guy who told us to read the instructions?
Yeah, that's what happens.
That's
Remember, the world is built of hypocrites, and I am the greatest of them. Well, that's that. So that's essentially all we really need to know. This homework assignment is a really good tool to prepare yourself for the test, in my opinion. And I'm sure that's the whole point of it. So I guess it's done its job well. So that's cool. Oh, so that's everything. So if we don't have any more questions, then I will I'll end this and post the recording on YouTube for those lowly plebeians who didn't have the time to attend. Unfortunate. Well, they'll get to watch it if they so desire, I suppose. So I will hit that button. Nope, that's the wrong button. Go like that. And then